Welcome back, everybody. So in this video, it's the last section of basic trig equations. We're going to talk about the general solution. Now, up to this point, when we were talking about solving trig equations, we were looking at it in a specific interval. But now I want to find all of the solutions, and I'm going to have to represent that in a kind of creative way. So to get a sense of why, let's take a look at these graphs for a second. So here's cosine theta, and I'm looking for when cosine theta is equal to negative the square root of 3 over 2. So I'm going to graph both of these values. Cosine theta will come up in blue, and negative root 3 over 2 will come up in red. And when I look at that graph, I can see that familiar cosine curve, and it looks like I have 2 points of intersection. So I'd expect 2 solutions to this equation. However, this is graphed only between 0 and 360 degrees. If I change my window to include more values, like say I want to include negative values, say I'm going to go from negative 720 up to maybe 1080, and I regraph this, I notice that I have way more points of intersection. So in our basic 0 to 360, this is that window we were just looking at it in. I can see those two. But then those solutions come up again here, and again here, and again here. And in fact, if I change this window from negative infinity to infinity in the x direction, there's an infinite number of points of intersection. But we can get creative as to how to find them. That's because this cosine function is periodic, meaning that these values repeat themselves. And if I look for this solution, if I move one period later, that's where my repeated solution comes up. And understanding that period is how we come up with the general solution to this equation. Now, the cosine function has a period of 2 pi. That's because if I go 2 pi around, or 360 degrees, if we're talking about degrees. And then it's if I go 360 degrees around on a circle, I wind up right back where I am in terms of angles. So it's really representing the coterminal angles to the cosine function. So when we go to solve this, we actually start by solving the basic solution like we did before. So I'm going to first find all solutions between 0 and 360. Find all solutions in one period. So that's on the interval 0 to 360. And then I'll get all of the repeated values by looking one period later. So we'll start with identifying the sine, since it is negative. The quadrants in which cosine is negative, a smart trig class. Cosine will wind up being negative in quadrant 2 and 3. So my quadrant would be quadrant 2 or 3. And the reference angle that'll give me root 3 over 2 will be 30 degrees for cosine. Okay, so I need 30 degrees in quadrant 2. So it's 30 degrees back from 180. Give me 150. And 30 degrees in quadrant 4 is 30 degrees past 180. 180 plus 30 will give me 210. Now those are the basic solutions between 0 and 360. 150 and 210. Those are my basic solutions. But because cosine is a periodic function with a period of 360, if I were to add 360, I would get another solution that corresponds to this. I could also subtract 360 and get an answer that corresponds to this. And once I get that value, I could then subtract another 360. So in reality, I can add or subtract any multiple of 360, where n is some integer. Some integer multiple. Similarly, from 210, I could add or subtract 360 degrees in any multiple of times, again, n being some integer, and this set winds up being the set of all possible answers to this trig equation. Again, looking at the graph, we can see, so 150 degrees, that's corresponding to this coordinate here. And if I go 360 degrees past that, that's where its value repeats in the second period of cosine. And if I continue another 360, it shows up again, which is why I can add or subtract any multiple. If you were doing this in radians, it's very similar. I would do 150 degrees in radians is really just well, we could do 30 degrees in radians would be pi over 6. So then if I'm doing that, it would be 5 pi over 6 would be my 150. And if we're doing 210, it's going to be 7 pi over 6 if we do those conversions. And rather than adding or subtracting 360 degrees, the radian equivalent of 360 would be 2 pi. So I would add or subtract 2 pi n in each of these circumstances. And that would give me the radian equivalent of the general solution. So since I was looking for degrees, this is my answer in this case. But had you been looking for radians, same process over here.